All right, let's look at the precise definition of a limit. All right, so remember that so old definition and so limit of f of x is equal to L as x as x approaches a is equal to L if the value of f of x function value can be made arbitrarily close to the limit value L by taking x sufficiently close to a, but not equal to a, from both sides, right? So all we need to do is translate that into a precise math notation, right? So that's what the precise definition is. All right, so let's look at the precise definition. So this is the two-sided limit or both-sided limit. Limit of f of x as x approaches a is equal to L, right? So if, right? So here's the thing. All right, so we want to say, so we want to define precisely what we mean by arbitrarily close, right? So close means that the distance is small. So what it said is that so this is the notation for all. So here, so this means for all. For all epsilon, a small positive number, right? There exists, right? So this is a lazy math notation for, because we can't spell. There exists, right? A corresponding delta value, positive delta value, such that, right? So here is the translation. All right, so I'm gonna kind of go backwards. So by taking x sufficiently close, so how do we describe that? Is this, all right, we're looking at the distance between x and a, right? And the reason why we put the absolute value is that we don't want to, because since we're talking about the distance, so we want the positive difference, right? So this is basically the distance between x and a is less than this small number delta. All right. The reason why it says greater than 0 is that here we don't want x to be equal to a because limit does not care about the function when x is exactly equal to a value. Right. So it's positive because we don't want the x to be equal to a, but the distance between those x and a is less than delta, right? So x and a are close, sufficiently close. This implies, so this is my lazy notation, so this means implies that the distance between the function value and the limit value, right, and can be made arbitrarily close, means that the distances can be made small as we want, right? So so the small means less than epsilon, right? Remember that the epsilon is any positive number. So if you want to choose epsilon to be 1, that you can do that. Or we can choose epsilon to be 0.01 or even smaller, any positive number. So what we need to be able to establish is that somebody gives you a really, really tiny distance or a tiny value for epsilon, which is the distance, the distance between f of x and L has to be smaller than that. We have to show that we can always find the corresponding delta value, which is the distance between x and a. So if the distance between x and a is less than this delta, we can guarantee that distance between the function value and the limit value is smaller than the given epsilon value, right? So this is a direct translation. I know that it doesn't look very nice of the definition we had before, right? And I want to talk a little bit about the one-sided limit too, right? Because the definition is pretty much the same. only modification you have to make is that everything else is the same for, say, here. Right, this one for two-sided limit. Right, the reason why we have this say absolute value sign. If you don't like the absolute value sign, we can rewrite this. So this is going to be the same thing as x is between. A minus delta and x and smaller than a, or bigger than a and less than a plus epsilon. Because you can go, either way from a. So x could go bigger than a or smaller than a, but we have to make sure that it's a smaller than a plus epsilon, or actually, I messed that up. Not epsilon, delta I meant, right? And then we also have to make sure that it's bigger than a minus delta, right? So if you want the left-hand limit, all you have to do is replace that with only the left-hand side. So we'll replace it with a minus delta is less than x. X is less than a, right? So we just need to replace this guy by only half of it, right? And of course, right-hand limit is x is between a and a plus delta, right? So for right-hand limit, you replace this absolute value 1 with only one side. All right, so that's the precise definition of a limit. All right, so let me try to explain what we're trying to say. All right, so here's the picture. All right, so we want the function value to be, less than epsilon away from the limit value L, right? So it's going to be between L minus epsilon and L plus epsilon, right? So that way the distance is always is less than epsilon from L, right? So this is sort of like the acceptance region, right? So we want to be smaller, function value to be smaller than this value, L plus epsilon. And we have this epsilon, L minus epsilon. So we want the function value to be bigger than that value. So you can see that the acceptable function value is coming from here and between here and there, right? So we accept those guys, right? So in order to have those values, how close does x have to be, right? So to how close to a does x have to be, right? So you can see that here, I'm going to just pick a kind of a reasonable delta value, right? So we can go away, so delta this way, which gives you a minus delta. And if you go to that way, delta, so we have a plus delta, right? So if you can see that, if the x stays between a minus delta and a plus delta, and you can see that here, if you go up, right? If you go up, if x stays in between those two guys, right? Then the corresponding function values stays between L minus epsilon and L plus epsilon, which makes sure that the distance between f of x and L is less than epsilon, right? So in this case, if you can do that for any epsilon, so some people might choose epsilon to be very, very small, but we can always find the corresponding delta, right? So then the limit is going to be L, all right? So what if the limit doesn't exist, like this one, right? So here, we don't know which value to be a limit value, so I'll pick maybe this value to be, for example, a limit value, right? If you go to um, epsilon up and epsilon down, so I put LL plus epsilon. Sorry about the notation. So this is going to be a left-hand limit, so I put the L there. LL minus epsilon, right? Then you can see that here's the acceptance region, sort of, right? So we want the function value to be between those, right? As you notice, if you in this case you cannot find the delta value because of these guys up here, right? Because no matter how small you pick delta, so let's say here is my delta, and so here is a minus delta, you have a plus delta, right? So no matter how small you pick, right? And these guys up here is going to stay outside the acceptance region, right? So the limit doesn't exist. But if you look at only the left-hand side, you can see that left-hand side stays, so left-hand side is right here, right? So there it stays in the acceptance region. So the left-hand limit is going to be this LL, right? And the same way, right-hand limit, if you're approaching from here, the limit value is actually up here, right? But you can see that if you're approaching from this side, you can get close as close as you want. So the right-hand limit exists, which is up here, and the left-hand limit, which is down here, right? All right, so that's the precise definition of a limit. I know that the notation is kind of scary, but all it's doing is that translating what we had before into a precise math notation, right? So it just takes a little bit of getting used to. All right, that's it. I hope that this was clear.